All right, Jim Laris, how are you doing?
Good. How are you?
Good. It's been a while since we've talked, since the Singularity days, actually.
Right. We did, I think, 3 videos for Singularity on ch9. They were pretty popular.
So you've been, of course, really busy in the cloud computing world, and you guys released a paper recently about a new framework called Orleans. So what's going on here?
Yeah. So since Singularity, I moved over to a new project inside Microsoft Research. It's called the Extreme Computing Group, and we're doing a lot of things, but a lot of what we're doing is centered around this idea of client plus cloud computing. Basically, we see the future platforms as being not just sort of devices that are sitting there and not just the cloud platform, but this combination of lots of really interesting devices, not just PCs and phones, but special purpose devices, things like Kindles or your car or your refrigerator, or sort of all of these devices which are easy to wire together today. It doesn't cost very much to add a processor and a wireless connection to a piece of hardware. And so you have this sea of devices that are out there that belong to you. So how do we put them together? Well, we also now have this cloud computing capacity that you can, walk up to Azure and you can go and get as much computing and as much storage as you need on demand. And you can expand and contract it as your demands contract. And so we finally have the pieces to build really interesting distributed systems. It used to be if you wanted to build a distributed system, you had to go and sort of get a lot of machines, you had to get a machine room, you had to get a bunch of people to maintain it, and it was like a real hassle, and only very few people actually were capable of doing this. Now anybody can do it, with a credit card, of course. Anybody with a credit card can do this. And so this gives us the potential to build this new platform. And so a lot of what we're doing in the Extreme Computing Group is looking at this as basically a new way of doing computing and looking at all aspects of it. Starting with how do you build data centers that are more efficient and cheaper and more power efficient, so that as it becomes more popular, we don't use an increasing amount of energy and don't cause lots of bad effects with climate change. So we're looking at that. We're also looking at how do you program it inside the data center. And that's what we're going to talk about today, is the programming model that we have for Orleans. But we're also looking at the clients. We're really interested in sort of new hardware for the clients, so that you don't just have phones that look like your iPhone or your Windows 7 phone, but actually have much more interesting user devices that allow you to do more than just sort of pretend you have a keyboard on a very small screen. So we're really looking across this whole spectrum of things.
Excellent.
But, key to anything like this, of course, is how do you program it?
Yes.
Right. And that's what this project has been focused on, is trying to deal with the real difficulties of it. And it's a really challenging environment for programming. We have a distributed system. You have a lot of computers that are physically separated that communicate by exchanging messages. That's, within the data center, obviously, there are, tens of thousands of individual computers, and if you're building a service, you have to use a large number of them. And so you have a large number of independent computers, which means that they're going to fail. You sort of have to expect that as a norm, that the computers will fail, the networks will fail, disks will fail. All of this just is sort of par for the course. And then you also have parallelism, is that all of the individual computers that we're programming are multi-core these days. So in the data center, we're up to 6 or 8 ray parallel multi-core. On devices, we have several computers, typically a couple of processors, and it'll grow as time goes on, because that's the way you get power efficient performance on things, as you build many low power cores. And so we have this difficult programming environment, and we're also asking people to build very available, highly reliable services. So if I'm going and building a service that backs up my application, and I'm really lucky, and all of a sudden 100 million people are using it, when that service fails, you get in the newspaper.
Exactly.
It's not like a crash on an individual person's machine, which is maybe too bad for that person, but it doesn't affect 100 million people at once. It used to be only the phone system could crash, or the electric system could crash and do this. Now, if sort of a major service, Facebook or Google or Microsoft, has an outage, that's the kind of thing that gets reported in the newspaper, because it affects so many people. So how do you build software that's that reliable? Or how do you build software that can accommodate 100 million people? Right? This issue of scalability is a big, big challenge. You have to be able to build things that can grow by orders of magnitude. If you're lucky, you're having 10 times more users than you had the week before, but that's like a huge challenge. You can go get the machines, if you have a credit card. But how do you write your software so that it can grow 10 times in a factor of weeks? There are some best practices that are known. You want to try to avoid bottlenecks. You want to try to avoid centralizing things like data. You want to try to spread the work across many machines. You want to try to do load balancing dynamically and things like that. But it's a really challenging world to write software for it. And so this project is really about trying to take many of the best ideas and best practices and building a framework that will allow developers to come in and write software that will have the desirable characteristics, that it will be available even though it's running on an unreliable platform. It'll be scalable so that if you're successful, you can grow pretty quickly and sort of, you may have performance bottlenecks, but you don't have to rewrite the system.
Excellent.
So, what we view it is as a sort of higher level programming model. So much as the .NET framework is to Windows, we see ourselves as providing a level on top of a system like Azure, which gives you a higher level programming model, sort of a large library of functionality that's common to many users, plus sort of a more forgiving world to program in.
Excellent. And so we have lots of the people who've written this and thought about it. So let's go around and introduce yourselves.
My name is Gabriel Cleot, and I work with Jim for the last year and a half on this project.
Excellent. Are you a developer?
I'm a developer on this project. Yeah.
Excellent.
I'm Ian Talene. Again, I'm a developer. I think we're all basically cutting code on this project.
Engineers everywhere. Yes.
All engineers at heart. I've been on this project about a year. Before that, I was in Connected Systems Division and Windows Live, so trying to apply some of that experience.
Excellent.
Hi, my name is Sergey Baikov. I'm a development lead on this project, and I've been in it almost since the inception.
Nice.
Watching.
And of course, we know Jim.
I'm Alan Geller. I'm an architect on the project. I've been working on Orleans for just over a year.
Nice.
Hi, I'm Ravi Pandya. I'm also an architect on the project. I've been working on it for about a year myself. Was at a different incubation project before that for a few years, and then before that in Windows.
Excellent, man. So let's talk a little bit, let's dig in now, because this is a managed framework, .NET, running on the CLR in the cloud. You guys did all of your rocket science above. Can we dig in a little bit about since you're architects, the design decisions to go with promises? Just jump right into this. People will read the paper and kind of understand. So can we talk about how you thought about why you decided to incorporate certain concepts, actually? So the average .NET developer out there doesn't really know what a promise is. They're not used to programming asynchronously using that concept, but it's a pretty easy concept. So can you talk a little bit about that? So we're going to be random and jump right into various spaces.
Sure.
Then we'll get into grains, the morphology of grains.
All right, so promises are basically an asynchronous programming model. It's been around for a long time. It's starting to get more use. And the idea is that when you invoke an asynchronous operation, what you get back is a promise for the result, and you can use that. You can use that promise. You can send other operations to that and queue all of those up, and then at the very end, you can wait and have a continuation that will be invoked when that promise actually gets resolved. And so that allows you to have several things going at once, and also control what happens and in what order when it actually happens. We also integrate this into the messaging framework, so that you can send a message to a grain, get back a promise, which might be for another grain, send it a message, get back a promise for that result, and so on. And you can send a bunch of messages, and those will all be queued up in various places, and then you finally, when the result comes back, you can take another action based on that. One of the key things that gives you is that it compensates for latency, where in a distributed system, one of the big problems, if you try to treat it as a simple synchronous remote procedure call, every time you make a remote request, you go out, you have to wait for the result to come back, you wait for the next result, and so on. And that is typically actually the major cost in terms of the time that elapses, because the actual computation is typically very small compared to the amount of time it takes a message to get from one point to the other and back. And so with promises, you can essentially pipeline a whole bunch of requests, and then while those are executed, you can have other things happening in parallel, and it makes the whole system much more efficient and increases throughput.
Cool. And so I guess I kind of jumped into it pretty fast, but I mean, you guys, which is fine because I think that's interesting. In terms of like your model of grains, maybe we should talk about your architecture a little bit about the grains and things like that.
Sergey.
So yes, grains is one of the key concepts in Orleans. And in some sense, it's easy to explain what a grain is. In another sense, it's not that easy because there are so many things that are similar. Because grain is a unit of computation, a unit of state, a unit of placement, distribution in the system. And to a large extent, to some degree, you can think of it as a remote object. But it's not a remote object at the same time. So all grains are isolated. They cannot share memory. They cannot talk to each other. It's all message passing between them, which allows the system to place them pretty much anywhere in a distributed system of multiple computers, multiple servers. So you have thousands of servers, and if you have these isolated units of computations, you can move them around and place them to optimize for the overall system performance, not just for your very narrow piece of computation. So this graphically, you could probably visualize this as your application being a sea of grains, these pieces that contain some state, some data, and they talk to each other because they're isolated. They talk to each other through message passing. So they exchange messages. And because they can run on different servers, different computers, everything is asynchronous in this world. That's why we go with promises, because anytime you make a call to another grain, it's a remote call. The latency of it is not known upfront. You cannot. It'll be inefficient to block and wait.
Sure.
Right? To get a scalability out of the system, in the system we create multiple replicas of each grain. So grain is a logical concept. It's an object. For example, you have a user account or a catalog item. That would be a grain. But if you have a catalog item that's very popular, for example, you have an e-commerce website and you get a lot of millions of requests for a popular catalog item, it'll be hard to service those requests from a single copy. But the system can automatically create multiple instances of this grain. So you'll have replicas of the same logical grain will be physically placed in multiple machines. And what's important is that it's doable today with traditional tools. You can write programs, you can run a system that does that, but you'll have to do all this manually in your code. You'll have to take care of all these issues. So one of the main goals of Orleans is to make it very simple for developers. So you program in terms of logical entities. So you find grains, like in this example, catalog item. But the system, the runtime behind, will take care of scaling out, replicating grains, so that you can get scale sort of for free. So it solves hard problems for developers as opposed to having developers solve those problems, because it's really difficult to solve them right.
Much like memory management is for the garbage collector and .NET in general and TypeScript.
Exactly.
So interesting. Now a grain is not an object, even though it sounds like an object. It's not. Right? It encapsulates a bunch of something, and then you can instantiate instances of it, but it's not an object.
So logically, it looks like an object, but physically, it's more than an object.
Okay. Excellent.
So what is an object anyway?
Okay.
I mean, if you could settle that, then we could tell you why it wasn't an object. But the key thing is, I think that there are a couple things that beyond what Sergey said. So key thing is that the only way you can access a particular grain is by sending it a message, and it'll send you back a reply. And so the question is, how do we handle the processing inside one of the grains? And what we've done is we've taken a very simple model. We've said, this is a difficult world, so let's simplify this as much as possible. So with inside a grain, we have a single-threaded model. So the grain gets a request. We basically expect the grain to do the processing on the request and then reply before it goes and pulls another request off of its message queue. It doesn't seem like a very concurrent model, but what we expect is we're going to get the concurrency by having multiple activations of the grain. So instead of sort of having each grain trying to be internally concurrent and then have to do all the locking on its state and worry about all the parallel errors that can occur, we just say, look, the grains are isolated. It's really easy for us to go and sort of have multiple grains executing at the same time. That's a model that people can understand. It gives you the scalability, and it also gives you something else. It gives you replication, and so you get failure tolerance that way. So, if we had a grain that was providing an essential service, even if it wasn't heavily used at a particular point, we might want multiple copies just so that if one fails, the rest could just pick up the load and sort of continue transparently.
So one question I have then is, do you create these grains by policy, or do you have some way of knowing that we need to create 50 instances of this grain because of X, Y, and Z? So in other words, what's the state machine? What's the
Sure.
the logic?
The simple answer is yes.
Whatever you want.
Yeah. So this is an area where we're actively researching. Right now, we can do it by policy. We have some very, very simple policies that we allow the developer to express. The policies we currently support will probably actually get rid of because they give the developer more control than they really should have.
Wow.
It's the wrong level of control. They can say, create one here. That's not really what the developer should be thinking about. They shouldn't be thinking about a machine. They might be thinking about, I need to access this grain, and I'm going to want that grain to access, a very, very large data file that's on some server. Or that there's some piece of information, and so if it can tell us that, then the runtime can say, okay, I know how I know where that data is. I know how long it will take to construct a new activation of that grain on the same machine where the data is, if that's an option, on another machine close to it, on a machine far away from it in a network sense. What's the most optimal place to create that activation? Is it on the same machine, or is that machine really busy and it'd be better to put it somewhere else? The notion is by giving the developer kind of just enough ability to tell us policy, to specify kind of what things are going to go together, then the runtime will be able to make an educated decision to put things in the right place so that the system as a whole will perform well. And provide the scalability, reliability, all those things that we need to.
So there's not going to be any sort of finalizer conundrum that we had with the garbage collector in .NET when it first came out, remember? So giving developers control, because this is such a complex thing. We should talk about, I'm going to turn the camera this way because these developers over here are being awfully quiet. So, you got, I don't know exactly what you worked on, so my next question is going to be around the actor-based kind of concurrency model that you guys implemented, but we can ask you something else. Talk to me, man.
So just maybe to add something more to what Alan mentioned.
Perfect.
So one of the policies could be that the programmer will basically specify, I want this amount of throughput for this grain, I want this grain to be able to handle this amount of requests per second, and we automatically measure it at runtime and create multiple copies of the grain, multiple activations to withstand this throughput. So the programmer does not need to tell us how many grains to create, he just declares his quality of service basically.
SLA.
His SLA, yeah.
Okay.
So this kind of resource management that we are intending to implement.
Excellent.
And then you asked about the...
Well, this is actually brought up a different question. Would be, how do you synchronize these things? So,
So a big part of this is when you create multiple copies of the same grain, you need to make sure they behave in consistent and transactional way, and Ravi is the best person to explain this.
Transactions live, man. Yeah. We'll come back. We're going to come back to you. Cool.
So what we did is, one of the big issues, since we do need to make multiple copies of these grains, is now if I'm sitting here and I'm sending a message, and one time I get this activation over here, and one time I get another activation over there, basically it's very hard to write a program under those circumstances, because I don't know if I've made an update whether I'm going to see it again. and then what happens in the cases of failure. And there's a lot of frameworks do basically just say, all right, throw up their hands and say, we're going to give you just eventual consistency. There'll be many copies. You don't really kind of know which one you're going to get at every moment, and you have to kind of deal with it. And that's okay if you're willing to invest the development effort to manage it, but it's a lot of work. And so, since one of our goals with Orleans was to try to put as much of the complexity in the framework as possible to make it simpler for the developer, we are trying to give them a more consistent view of the world. And the way to do that is essentially something that is transactional. Now, distributed transactions, fully serializable distributed transactions are expensive and they're hard to make reliable and performant. So we have a slightly sort of what we call lightweight optimistic transactions, and they leverage this fact that when you have there's sort of grains are these logical entities, and then they can have multiple distinct activations. So what happens is when a new request comes into the system, say a new web request or web service request comes in, it starts a new transaction, and every grain that it touches it touches an activation, and that single activation joins that transaction until it completes. And this gives it a consistent view of the world because it only sees one activation of any given grain until the transaction completes. And then in the end, we also isolate those so that an activation can't be part of two different transactions at once. If they're both read-only transactions, we can allow that, obviously, but if they're two things that might modify its state, they're kept isolated so that they don't interfere with each other. And then the way the logical grain model works, where you've sort of declared all of your persistent state, allows us to also deal with persisting those automatically and making them durable. And then we also manage when we make them durable, and when we expose them, we make these transactions effectively atomic, so that the change state of all of those grains is only visible when the transaction completes. Now, one of the things that makes it optimistic is that we kind of make this distinction between when it completes and when it actually commits. Most sort of traditional database transactions, those are effectively the same thing. So instead, we will allow a transaction to complete. You might have touched all these different activations, and then another transaction can come in and reuse those before we've actually committed those to disk. And we do some careful bookkeeping to ensure that what gets exposed is effectively atomic, so that it only sees a consistent set of all of the different activations that were involved in that transaction. And then when we also commit it to disk, we also make sure that what gets written out is effectively atomic. And this has some interesting issues, because one of the goals for this was not to insert any blocking points in the operation of the transaction. So we try to sort of proceed optimistically as much as we can, and then we may later on discover that something went wrong, and then we might need to abort and retry the transaction. Most of the time it completes successfully. We come back, we can hand back an optimistic result back to the client. If later on we end up having to abort and retry that transaction, it might get a different result. For a lot of things, that doesn't matter. I mean, if you're sort of looking up, let's say, recommendations to go along with the catalog item, okay, if the result would have been different, that's no big deal. And for things that actually matter, you can say, all right, if it needs to be retried, wait, don't tell me the actual answer until it's actually committed for things that are more important. So, to give you an example of one of the issues you can run into, can you pass me a pen? So if you have a request that comes in, let's say for grain A and activation 1, and it goes off and it calls grain B activation 1 and grain C activation 1, and these all talk to D.
Okay.
So the easy part is that if they all happen to pick the same activation, that's cool. They've all seen a consistent state of the world. Is there an eraser? However, and if this happens sequentially, what happens is we sort of keep track of as it flows. It goes to B, goes to D, comes back up, goes to A, goes to C. We're sort of, as it accumulates, we're keeping track of which activations it's seen. So if we flow down here, we go there, we realize, all right, and then C comes and says, I need to send a message to grain D. It says, okay, cool. D1 is already part of the transaction since we have this history, essentially, that's been tracked as these messages flow through the system, so I'll pick that. However, this could also be happening asynchronously. So that what happens is, these are all happening at the same time. A1 sends a message to B1 to C1, and those are happening concurrently because it's asynchronous. And these could be on different machines. And so, at some point, we try to kind of have some heuristics to help these guys choose the same activation of grain D, but they might not. So C1 might choose to see D2 and B1 might choose to see D1. But then what happens is they start returning their responses back here. And then at this point we realize, uh-oh, we have D1 and D2. And that's no good because now you've seen an inconsistent state. Or you would if we let A1 continue to execute. So at that point we say, okay, we can't proceed. We have an inconsistency, and we're going to abort this whole transaction. But what we do is we'll retry it later and try to avoid this in the future. And so what we record in the retry log is also, all right, we had this inconsistency in grain D. So then what happens is when we go through and retry it, before we even start, we'll pick D1 and join that into the transaction, or pick some D1, D2, D3, whatever, and come through and now B1 and C1 are guaranteed to pick the same activation, and those will proceed. Okay. So this is sort of an example of some of the issues that we manage, but the end that we have to deal with. But the end result is, as a developer, you basically you just see a consistent state of the world. Your code just sees it sees all of its writes. It sees a consistent state of any other grain that it interacts with. One other nice thing about having this be transactional is it helps deal with error handling. When you're dealing with a distributed system and everything's happening asynchronously, it's really hard to recover from errors. It's hard enough in synchronous code with try-catch and trying to undo any effects of stuff that went on. But when now you've got several things going on, several things might or might not have completed, you don't know if you need to do compensating actions or not, it gets really difficult. And even if you take the time to write the code, it's hard to test, and so
Sure.
even that's also very error prone. So instead, you can basically not worry about it. If there's any kind of a failure, we'll just abort the transaction, we'll retry until it succeeds, or it will just atomically fail. And so then all you really need to do is do error handling sort of at transaction boundaries, and those are much fewer. And all your complex operations that might run across multiple grains, they don't have to deal with it. They just run you through and do your straight line, assume success kind of code. And it's much simpler for the developer.
Sure. No. I'm glad you guys are doing that. It's always been kind of weird. Now, inside of a grain itself, it's going back over here because I said I would. The grains themselves internally aren't concurrent, right? So.
Instances of the grain are not.
Yes. So talk to us a little bit about the morphology of a grain.
The morphology of a grain. It's a philosophy.
Is that a fair question?
Yes, I'm a philosophy. Philosophy.
So I mean, because we talked up there, essentially they encapsulate anything from a search index to some simple computation.
Yeah. I mean, that's one of the key questions that we're still trying to work out is what's the right level of abstraction? Is this like a table row, or is this a whole table, or is this a big chunk of computational logic? And unfortunately, the answer is it's all of the above. And so we're trying to provide a little bit more assistance to people, so that people beyond this room can actually start using this.
Good.
We've kind of got the hang of the system. We know those kind of sort of trade-offs, but the difficult choices. And then, as people have alluded to, there's all the question then beyond that of how do you specify what your actual requirements are from like policy, activation policy, those kind of things. So there's a lot of areas that we're kind of starting to look at as we get this to go more usable by more people. Than
Sure.
Just the 5 of us.
Understood. Now, the .NET framework, this is, .NET 4, you guys wrote it in C#. My question would be, the CLR and underlying platform really wasn't necessarily designed to run a system like this, one could say or one could not say. Did you have to have any help at the CLR level for like garbage collecting grains and stuff like that? No.
Actually, the CLR .NET is a good platform for this. We haven't made any changes to it. It's designed and engineered to run on servers as well as on client
Sure.
machines, and certainly we're running it on servers, and we've gone and had to do some work around the edges, but nothing that's sort of integral. It's worked very well. In fact, we're even looking beyond C#, and there's interest in getting our Orleans framework to work with F# as well.
Cool. Well, that would be nice.
Yeah.
It's beyond interesting.
It's beyond
There's
interesting.
a developer here who
Yeah.
has working F#
I guess that's right.
Orleans code.
Yeah.
Nice.
So,
And I suppose anybody who was interested could do VB code as well.
sure.
Sure. I mean, you can, right? I mean, it's all
Yeah.
IL
Yeah.
anyway that
Yeah.
you're spitting
It
out.
works. Yeah.
So you can write it in
Absolutely.
VB.net.
We could.
Now, at the PDC, just to throw in a kind of a fun wrinkle before we kind of dig into more things here, Anders and company invented or added sort of async support using futures,
Yep.
sort of futures in C#, right? The async keyword,
Yep.
blah, blah, blah. How would that work? Are you thinking about how you could work your
Yeah,
modeling with that?
we're definitely thinking about it. We're very excited by the async extensions to it, and we'd very much like to sort of bring it into our system and use it as an integral part of the system. We're programming in an async world. Seems like a very nice way of sort of expressing what's going on. We haven't done it yet. Quite exactly how we're going to merge it with the promises, I don't know. But the async is designed to be extensible, just like Link was designed to be extensible. There's an interface level below it, and we'll take advantage of that and build on top of it.
Very cool.
One thing is it's built, the async framework is all built on the TPL.
Yes.
And
it is.
everything we have is also built on the TPL.
It is. Interesting.
And you can also think about it as we're extending this asynchronous model, which is kind of built for local computations to a distributed case. Because in case of grains, the grains talk to each other through things we call grain references. So it's like a logical reference, logical pointer to grain. But it also has asynchronous characteristics. For example, it can accumulate requests while a reference is being resolved, because everything is dynamic. You have a name or an ID of a grain you want to talk to. And to get a physical address of it, it takes time, latency to resolve the physical address, the server address through the system. But while that is happening, you can start sending requests and get promises back. So it's kind of the next step of extending asynchronous programming model to distributed world. So you get all the same benefits transparently, including error handling, which is also, like Rob mentioned, very important. Because with the model we use with promises, you can put error handling at the right level in a distributed world, which is really nice when you can say something similar to try-catch, not quite try-catch, but at the transaction or at the high-level, request level, and catch all the errors and not worry about them at every single statement.
Wow. So a promise will either definitely come true or not, right? It'll be resolved, returned, or just nothing.
No,
Right?
not quite that. It's actually even better than that. It'll either come back with the result that you were expecting, or it'll come back with an error that you can basically distinguish the two,
Cool.
and you can handle separately. So you can basically say, run this computation, give me back the promise, and if it works normally, I want to do this, and if it fails, I want to do it this way. And it's a very clean hand way of doing, in essence, what's an asynchronous catch.
Okay.
It actually has a couple of other interesting properties. One of them is that it's composable. So you don't have to handle each individual error as it goes along. What happens is the errors propagate through the data flow. So if I send a message to a directory to get a file, for example, and then or to get a subdirectory, then to that directory to get a file, and then I open the file and so on. And then at the end, I have this promise for, let's say, the first chunk of data in the file. That's the first point at which I actually want to do anything. I can just issue all of those requests, and then at the end, take a look whether that the block of data succeeded, and I can process it, or it failed, and I can handle the exception. And the errors propagate basically through the data flow. If you think about, it's very similar to the way if you're writing a spreadsheet, you have nans or errors that will propagate through the spreadsheet. When there's an error, it's the same thing for promises, where they propagate through the data flow of all of the requests or other operations you have queued up. And it gives you a very, very nice way of matching that to your program flow, where synchronous try-catch just doesn't make any sense in an asynchronous world.
Sure.
Maybe we should give an example, because
Yes.
I'm a little bit worried that when we're talking about sending message, people may get it differently than it really is. So when we say send message, when you write code, you really write a method invoke. So you call a method. Under the covers, it sends the message. But as a developer, you don't deal with literally sending messages and receiving messages.
Sure.
Likewise, if you write in a grain, when you receive a message, you receive it as a method call. So you implement the method. It's not like you have a handler or message pump.
Sure.
Right? Maybe it would help to kind of show
Sure.
a couple lines of code just to
Absolutely.
illustrate that. Let's take an example of reading directory and getting file and reading data from a file as kind of a canonical example of three-step process of doing some computation. So imagine you have a reference that you obtain somehow for the file system. So you have a file system grain somewhere, and you want to get a directory first, right? So you do get dir and pass some arguments. What you get back is a promise. So in this case, it would be a promise for a directory. Let's call it dir. This operation is asynchronous. So the method called getDir, which we refer to send a message to the grain, it returns immediately. It returns a promise for a directory right away.
Okay.
Without waiting for the actual result. And what you can immediately do, you can say dir.continue with and schedule the next step of your computation. We use lambda syntax, but you don't have to. You can use like traditional delegates.
Okay.
I'll just use kind of how we write it. So you get back, eventually you get back a directory object, a reference to a directory object. And you can schedule, for example, if file grain equals the promise for a file, directory dot get file, and pass arguments.
So actually, it might even be simpler if you thought of directory as a grain itself, and then you could just directly say dir.getFile without the continue with, and so a series of grains, and in the end you might have a promise. Yeah.
I'm just showing the
Yeah.
Sure.
Back to the philosophy.
Yeah.
It's a question of philosophy, what great is. Again, when this happens, which happens later on a different thread technically, when this operation happens, it returns right away. It returns a promise for a file right away. And again, you can schedule. You can say file promise.continue with. Again, using lambda syntax, and do read and get some data. The important point is that you're building this data graph, the computation graph, before data actually comes back, before you get the results. And you can pass two lambdas or two delegates, one for success case and one for the exception case. So you can pass like two functions, one that gets executed when the operation continues, completes successfully, and one that receives the exception in case of error. And you can do error handling in the exception block. And you can do it on the last promise you receive, because all these promises will be linked together. So promise for a directory, promise for a file, and promise for the actual operation. So say this is data. that you get from the read operation. So all these promises internally are linked together. So if get directory operation fail, this promise will fail as well. So you can focus on the last step and schedule error handling just for the last step, and not worry about handling the directory failures or get file failures. And you can return this as a result from your asynchronous method. So if this grain you're writing implements getting data, so you can return a promise for data and be done with your operation before everything completes. And the caller of yours will receive this promise, and this promise will get fulfilled or fail or broken depending on the result of all these operations that you sequenced or scheduled.
Yeah,
So
that makes sense.
Yeah.
I mean, it's not. This isn't a huge conceptual jump for your already existing developers. However, the client plus cloud computing, sort of the mesh thing. I mean, there's a little Aussie-ness around some
Sure.
sense. Is sort of a leap for your average developer to think about what it means to program in this context, right? So
Yeah, no, I mean, this is trying to hide some of the complexity. I mean, all of this can be running on different machines.
Yep.
We're sending messages back and forth. There may be a lot of retries because things fail. But if you're writing at this level, it's all sort of rolled up to you're specifying what you want. There's a little bit of asynchrony in there, so we don't give you the RPC illusion that everything is happening just like it would happen on a single machine, which is, a model that's been tried and proven to not work very well because people really think everything's happening on a machine and they write code like it is. In this case, it's pretty clear that there is asynchrony there, but it doesn't get so much in your face that the code becomes incredibly complicated. And you can handle the unusual cases, the exceptional cases, which come up in distributed systems all the time. You can handle them cleanly at sort of the right level of abstraction. It's a nice trade-off. You have to sort of find a good point there because there are a lot of different things that you want to do at the same time. You want to be expressive at the same time as you want to sort of hide some of the complexity. And we think we found a pretty good point here in terms
Sure.
of programmability.
And I think I don't think we give developers enough credit. I mean, developers tend to be engineers. They're smart people. They know what they're doing. They understand the languages and tools that they use. We don't have to always say, here, this one line of code will solve all of your problems. This is all you need to do. So I like that because I think sometimes we go a little overboard and, hey, make everything easy for developers. But these are engineers. So they can understand the complexity of the system that you've made easier for them to program.
Yeah, no, I don't think we haven't sort of reduced it to one line, as you could say.
Yeah, well, sure.
And we haven't hidden all the complexity either. But there's a lot of stuff that's really sort of below the surface. There's a lot of things that the system can do for you that handle the sort of normal case. If you were sort of a developer that was hell bent on getting the utmost performance, you might want to send messages yourself and deal with all the retries and everything else at the sort of lowest level of abstraction. This is not what we're aiming for.
Sure.
There are people that should be doing that, but most people I think would probably rather try to get something working at this level and sort of deal with the issues of performance once the system's working and deal with them in terms of adding resources as opposed to sort of going in and trying to get the utmost performance out of the particular piece of code. This is the trade-off that's made managed code so successful, is that machines are fast, they're relatively cheap, but people's time is not cheap, particularly
Absolutely.
developer time.
Sure.
There's a trade-off between scalability and efficiency in a lot of cases. It's not so much about what's the most I can do on one machine, it's how can I scale by throwing more resources at it, because it's cheaper to add more resources than to have more developers and more expensive developers. And I pay that cost over and over on the developers. I pay the machine once. So,
it doesn't make sense to solve the same set of problems over and over again with different companies, different developers. Because in the end, they're doing all the same work.
Yes.
So in all these big projects, high-scale project, a large percentage of resources or developers are spent on frameworks, on the foundation. So if you look at major internet properties, it's impressive that in many cases more than half of developers focus on building the foundation for doing actual application work on top. So if that work can be done once or condensed into the framework, all this developer resources that used to be spent on foundation can be used on building cool products, cool applications on top. Really focus on the client plus cloud, not on sending messages and dealing with failures.
And I mean, you guys are also addressing sort of what we take for granted from a hardware perspective, like in Azure, for example, or any other number of the cloud computing offerings, is scalability. So it's software scalability is what this is really all about, it seems to me. I mean, right?
Yep.
It's about writing some code that's going to scale automatically, literally automatically, because you've taken this model that you've encapsulated things in grains, things are isolated. There's not necessarily shared state. There is no shared state between grains.
That's correct.
There can't be.
There can't be.
So the isolation means you have robust, scalable system. This isn't about performance. We haven't really addressed that yet.
It's not about performance. I mean, the design of grains was to give the system, the Orleans runtime system, a great deal of flexibility to do things for you. So, the fact that grains are isolated means that we can pick up a grain and move it. We can do dynamic load balancing. We can spawn off another activation of the grain as the load gets too high. All of this can happen in the runtime system without the programmer intervention. So this is code you don't have to write. Hopefully it's code that we can build very robustly as part of the system. We can do a lot of work in terms of developing good algorithms that are sensitive to the performance, just like the .NET crew has been able to develop good garbage collection algorithms that deliver good performance on systems and reclaim a lot of the storage quickly. We would very much like to be able to do this in terms of compute resources as well. So can we expand the amount of computation that goes on and then contract it when the demand goes down so that you don't have to use additional machines? A lot of this is work that's to be done. I mean, we've scratched the surface on this. This is a huge project.
Sure.
We have a long list of things we would love to go and add to the system. Right now we've got the core part of the system running. We're working with actually a team inside MSR, the codebook team, to build their system on top of this. As part of it, we've gone and built a very interesting package, which is one attempt to sort of encapsulate very common functionality, and that's for handling very large distributed graphs. The type of thing that comes up when you're doing a social network, say, Facebook.
Okay.
The core of that is a graph, which is all your relationships to your friends and your friends' relationship to their friends. Codebook is a system that looks at social networking around code development, and so they have an even larger graph because it's not only the people, but it's all the pieces of the software.
Wow.
And so that graph doesn't fit on a machine, obviously. And so we got involved with them, and sort of one of the packages we built, in fact Gabby did a lot of the work on it, is a very large distributed graph package that is part of Orleans now.
So can we talk about that a little bit? I mean,
why doesn't Gabby
come on.
talk about it?
Yeah. So the graph library is kind of, on one hand, it's application above Orleans, and I'll tell about which grains it uses. On the other hand, it's a platform by itself. So people who want to have large graphs, the data organized in large graphs, and they want to store it in a large number of machines, they will use our platform. We provide a lot of functionality that makes their programming much easier. So they can concentrate, like Sergey said, on the algorithms and not on the distribution, messaging, replication, fault tolerance, or anything like that. So the idea is that we allow you to store data organized in nodes and edges. And nodes can be rich nodes, so every node has type, some metadata associated with it, versions and everything like that. And the edges represent relationships, which can also be rich, have types and metadata. And you upload your data, your data to the graph. We store it on multiple machines, organized in multiple grains. So we had the philosophical question: what is the right size of the grain here? We came to the conclusion that the best size for us is having something we call partition grains. So every grain has multiple nodes, which call it partition grain, and it can have like thousands or 10,000s of nodes inside. So nodes inside the partition, they just regular objects with regular references. Nodes between partitions need to use partition references. So basically, under the cars, will send messages. Okay. So we take the graph, we partition it to multiple partitions on multiple machines, and then we have a number of graph algorithms implemented. For example, you can easy stuff. You can just get the data back, the same nodes and same edges that you uploaded. But you can do much more complex stuff. For example, you can query this graph for patterns. you can say in the codebook case, the data is developers, bugs, fixes, file revisions, things like that, and you can ask, find me all the fixes to the bug which was opened by PM last year, which we're working on this team. So you submit a query which is expressed as a complex pattern over the data, okay, and we return you all the data that matches this pattern. So it's a regular expression type of queries. So this is one example of functionality.
Okay.
And as a developer, so that's but you can write more complex, like additional algorithms in our graph library. So we have a codebook team, which is our primary client now, which we work with together, and we have some other teams in Microsoft, product teams that are interested.
Good.
Because a lot of teams now have large data organized in graphs and would like to process it.
Sure. And I mean, in terms of, who would use it around here, who could use it, I mean, even ch9, may I say, people who want to build distributed services that are scalable, that are reliable, I mean, why not use this model? Why not experiment with it, right? Which brings the next question, which is, in a more traditional sense, not that what you just said isn't traditional, I mean, we have things like Facebook, but what about for developers who just want to build a service that runs on Azure or some appliance, or some cloud computing system, or they have pieces of it that aren't written with these things in mind. The other code doesn't know what a grain is, right? So talk about like an ASP.NET application or something running in this world.
Yeah. So I mean, one of the key value propositions behind this is what happens inside the Olean system is transparent to the outside.
Okay.
So you can use these grain references that we talk to talk to the system. You don't know whether this is on a local machine, whether it's on a machine inside your corporate network, whether it's on a machine running in Azure in the cloud. You use exactly the same programming model in all cases to do that, which is great for a lot of scenarios, even just the simple development test production scenario. That's a great scenario. But also you start out small. You get Slashdot story about you. Your website suddenly becomes really, really popular, and you have to scale up. You don't get forewarning of these things.
And I mean, in today's world, what you do is you go to your little, at least in the Azure world, you go to your command console. You type in, I know that I'm going to be busy because it's PDC, so now I want to allocate 20 nodes versus my typical 3. And then you have the hardware scaling problem solved, because it's going to run 20 instances of your app, and in some sense you're going to scale. In this case, it's really dynamic scaling because this underlying system determines that, hey, I'm being pounded, so I'm going to spawn off more grains.
Right. That would, that's the goal we're certainly working towards. Is that it'd be nice if you told us that you're going to get pounded next week.
But I mean, that could in some sense.
But some sense we can dynamically detect that. We can see the rate of requests coming in. We can see queues backing up, and we can basically go and activate more activations of the grains that have long queues. We can go and get more machines from the Azure pool and start them running Orleans, and we can go and bring up your system and try to maintain the SLAs that you want to maintain for your system. And conversely, when the demand falls off, everybody sort of goes to sleep or something like that, we can start releasing resources so that you're not sitting there paying for machines that aren't really doing very much. And so it's a much more dynamic model of computation that we sort of envision. A lot of the details hidden beneath the runtime system.
Excellent. So as we finalize here, what are some of the big problems you're working on as you move forward? I mean, you released the paper. It's a nice start.
What's next?
Yeah.
There's a bunch of different things that we're looking at. In the kind of the short term, we're very focused on reliability. How do we do persistence and different types of persistence? How do we do error handling? Not just at the we know how to deal with it in the programming model, but how do we deal with the machine going down and make sure that we roll things over properly, all that. More about scaling, as I alluded to earlier, kind of right now we have some policies around where do we place activations. We do have some logic in the system. We know what we have right now is stopgap. It's not where we want to be in terms of doing resource management, resource allocation. There's a lot of work to be done in that space. Geo-distribution is really important. It's anybody these days who wants to run a really large-scale application wants to run geo-distributed, both for client latency as well as for disaster reliability. And geo-distribution, because of the change to the network topology, to the network geometry really more, so the distance, not just the connectivity, really introduces a lot of wrinkles into both the reliability and the scale story. One thing that is a little bit longer term that I think is really interesting is, we talk about this as a client plus cloud solution. So one thing we'd like to be able to do is run Orleans on the client as well. I mean, it seems like a nice thing if you have a powerful enough client, which, smartphone is a powerful enough client, to be able to have maybe a grain activation run on your smartphone, because then when you go to interact with it, it's right there. And you eliminate that network latency. And having a system that will intelligently migrate computation between your client and the cloud would be really cool, and it would make a lot of things a lot easier, and there's a lot of really hard open issues there.
I mean, one of the things would be like how to synchronize grains when things change.
Right.
If you have the server changes, something happens, a grain changes its morphology or whatever, and that is reflected down on all the clients that rely on it. And somehow you magically synchronize that. It's a research problem that Gilad Bracco has been thinking about. We had dinner, remember, but it's an interesting thing. I mean,
there's that's one part. There's also just dealing with disconnection. I go on, well, these days lots of planes have Wi-Fi, but I go somewhere and I lose my connection.
Yep.
But how do you run in disconnected mode? Which is, again, there's a lot of people doing a lot of work in that for Ajax apps. We want to have that same capability on an Orleans.
There's a lot of security problems too.
There are a lot of security problems.
We can trust the servers in the data center to some extent.
To some extent.
How do you trust someone's cell phone?
Yeah.
Probably not very much.
True. So you have to say a few more things before we finalize here. What's some of the big problems you're working on? Maybe like 30 seconds each. We'll go around and then we'll let the Niners watch this, read the paper, ask questions that you guys will answer. And
Absolutely. I would say that there are two things that go hand in hand. It's scalability and elasticity. I think that's what Jim alluded to. So you have to solve both, and you get the benefits of both. Because if you're a big company running cloud operation, elasticity is really critical, because that's how you make money really in this business. And scalability is important for your application, so that the user experience is great. And the balance between those two and the right optimization, that's actually the holy grail of the whole project, I would say. Can you get to the level where you say what you need, like your service level agreement, and run this with minimum resources needed to satisfy those your service level agreement system. I think that's the holy grail we want to get to.
excellent. Not the holy grain.
No, we have one of those.
Yeah.
We'll rename grains.
Cool.
I'm looking at a lot of the the sort of areas that we've alluded to, particularly around the sort of management side of things. So if you have, for example, 1,000 servers, how do you deploy your application to those 1,000 servers? How do you upgrade them? How do you move something, for example, if you want to run it on-premise at the moment, but you later want to run it in Azure? Again, how do you deploy into Azure this exact same application code? And how do you sort of manage that once it's there? How do you find the problem areas? How do you find the nodes that are failing that you need to turn off and recycle?
Nice.
Interesting problems.
Very interesting.
For me, I would say the holy grail of Orleans is I agree with what Sergey said, but it's also the fact that we try to solve most of the hard distributed system problems in the runtime and not expose the programmer to even. He needs to be aware of them, he needs to tell us what he wants, but he doesn't need to write the mechanisms to solve those. So he doesn't need to write code to do replication, he doesn't need to write code to do fault tolerance. He must declare, he say, I want this data to be always persistent when it changed, or strongly consistent if you have 3 replicas, or like strongly consistent if that's what he wants, so weakly consistent with the transactional system. And we implement those mechanisms. And the programmer does not need to be a distributed system expert.
Excellent. Transaction man.
Yeah. So yeah, I mean that's a big part of what I'm going to continue to work on is the whole transactional model and how do we extend that to be able to make things reliable in the face of machine failure, network failure, data center failure, and also in terms of resource management changes as we need to scale across multiple data centers and multiple activations. There are a number of interesting issues there. The other things I sort of like to think about are what are some other interesting application areas for Orleans. We have the graph library is a great example of where we've built this general infrastructure to solve a large set of problems. Are there some others around things managing large data and compute intensive applications in the cloud? There's a whole other group within XCG working on scientific applications like the Azure Blast, for example, which was very popular at the latest supercomputing conference. And I think Orleans would also have some really great things to bring to that application domain.
Excellent. Now, what about, like, one last quick question, what about actually just implementing just a general purpose database using this methodology, so you wouldn't have this sort of problem of you have this big application and everything hammers a single database. I mean, that's essentially what happens in reality, right? I mean, the database is usually the bottleneck.
Yeah.
So if you had this kind of really distributed database model where you guys would, we're getting a lot of requests, we're going to generate.
Let me just jump in and say, that was one area we decided we weren't going to do. Microsoft has done so many cloud database projects, we decided we weren't going to do one of those.
That's what SQL Azure does, right?
SQL Azure does this, the XStore does this. We're going to use what's out there. We're trying, we're a small team. We're trying to sort of do what we can do well and hopefully build on a lot of other people's work as well.
Perfect.
But I would add that we address this problem differently. With the notion of grains, we encourage developers to split their state, split their data into smaller chunks, so you don't get into this bottleneck to begin with. So instead of kind of traditional approach, people start designing an application, you start with database schema. You design a table, nice, and just realize a couple of years later that the table doesn't fit database anymore because it's very popular. So with grain model, you don't think about it this way. So you define grains, entities, and their properties, and you don't end up with a single bottleneck of a database.
Cool. Well,
So we're trying to avoid this problem.
That's awesome. Very, very interesting project. You guys have kind of composed various already existing programming models like actors, promises, Erlang, message kind of stuff. Very nice. But this is a very unique thing, and I hope to see how this evolves over time. And hopefully people will get to play with it once it's in a state where that makes sense. It's a research project.
It is a research project. I mean, people should be clear that this is not a product.
Right on. And I must say the paper is very well written. I mean, I was able to understand it, which means, you guys wrote it very nicely.
Thank you.
All right. Take care, you guys.